So here we have the electromagnetic spectrum. As you can see, we have radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma radiation. These are the different types of lights. You can think of them as colors of light that you can't always see. Certainly you can see visible light. That's what our eyes see, the red through blue spectrum. You can also see that down here on the bottom we have wavelength. The longest wavelength is down here at radio waves, while the shortest wavelengths is over here at gamma radiation. You can see that we have a little graphic here showing us wavelengths getting smaller and smaller toward gamma. You can also see at the bottom we have energy, the lowest amount of energy down at radio waves and the highest up at gamma. So what happens when light and matter interact? That is, when a particle of light, a photon, runs into an atom. Well, when two things collide, you have several possibilities. The first is that they reflect off of each other, they bounce off. The second is they come together and stay together, one absorbing the other. Then you have the third, where one actually rips part of the other off, that going right through, a very high energy interaction. We're going to start with the easiest, reflection. When a photon comes in and hits matter and then bounces off of it, which leads us to the question, why is an orange orange? Why does it look orange to us? Well, if you're holding an orange outside in the sunlight and there's all the colors of light coming from the sun and hitting that orange, well, why are only the orange photons getting to your eye? Well, your orange will absorb the other colors and reflect orange. Your eyes aren't magical, they can only see the color that gets to them, so they see the orange as orange. Why is a lemon yellow? Same concept. All the colors of light come in and hit the lemon, and it is the yellow that's reflected. The other colors are absorbed. Now be very careful. Every now and again I'll ask people, why is a lemon yellow? And somebody will tell me, oh, the lemon is emitting yellow light. Nope, wrong answer. Emit and reflect are two very different words and have two very different meanings. Reflect means that the light is bouncing off. Emit means that it's giving off its own light. If you run into a lemon that's emitting yellow light, giving off its own yellow light, glowing like a yellow light bulb, you probably should leave the area because that is not normal behavior for a lemon. It might be hazardous to your health. The moon reflects. The sun emits. Why is grass green? Same reason, it can reflect green. Or, remembering that your eyes are not precision instruments, it could be reflecting blue and yellow. When those two colors come at your eye together from the same source, you're going to see it as green. If you need to separate the colors to see whether or not you're getting green or blue and yellow, you're going to have some outside means of doing so. For example, looking through a prism. Remember that a prism refracts light, so the two different colors will bend as they go through, and you'll be able to separate them and see them. You could also use a diffraction grating. A diffraction grating doesn't work quite the same way, but the end result is those colors are split apart so that you can see them. Interaction of light with matter means the emission or absorption of photons by atoms and molecules. So we're also going to talk about what happens when you get absorption and then later emission. Let's consider what happens when you heat up a solid object. As Planck found, it will give off all the colors in a spectrum, and if you look at it through a prism or diffraction grating, you will see what we call a continuous spectrum. All the colors are there. Of course, Planck also noted that you get more of one color than any other, and that depends on its temperature. However, if you have a hot However, when you have a hot gas and you look at it through a prism or diffraction grating, you don't get a continuous spectrum. Some of the colors are missing. You only see a few lines. This is called a bright line or emission spectrum. A bright line or emission spectrum is unique to the element or molecule that you're looking at, which means we can use it to determine what type of gas we're looking at. We look at a hot gas through a prism or diffraction grating and we see this pattern of lines, and we can match it up to a pattern that is known and determine what the gas is made out of. But why do we get only some of the lines? Well, the answer to that is in the structure of the atom, specifically the energy levels of the electron. Electrons in an atom exist in well-defined energy levels that are characterized by precise values of energy. That is, they're quantized. An electron can have specific amounts of energy. And like the analogy of a stair step, here it looks more like a ladder. Think of it like a ladder. An electron can have a specific amount of energy, but nothing in between. So your electron could have this much energy, or this much energy, or this much energy, but nothing in between. You can't stand between the rungs of a ladder. There is no place for the electron here. The lowest amount of energy that an electron can have is called its ground state energy, and electrons like to be at their ground state. Electrons have different energy levels depending on the element. You'll notice here that we have three elements, hydrogen, helium, and boron, and you can see the pattern of energy levels. Now, these are actually only a portion of the energy levels for each of these elements. They would go right off the top of the screen if we kept going. But it shows you that energy levels are unique to that element. So let's talk about what happens when a photon runs into an atom. In this case, let's consider a fake atom that only has 3 energy levels for its electron. Now this is much less than any of the real ones, but it makes it simple as a starting point. When a photon comes in, for example in this case maybe a very high energy one, ultraviolet or X-ray, then if the atom were to absorb it, it must take that energy in. Energy is conserved. It's neither created nor destroyed, so that energy that the photon carries must go somewhere. If it was given to the electron would have to jump way up in energy. Notice that long jump, which tells you very high energy. And it would be way off the top of the screen there. Is this one of the allowed energy levels? No. There's no energy level up there for this electron, and if there's no energy level for it there, we can't take it. Therefore, the atom will just reflect the photon that came in. So what if something lower in energy came in? Maybe sky blue. That means that if the atom absorbs that photon, it's getting slightly less energy, maybe this amount, and you can see if that energy is given to the electron, it will jump up to that highest energy level. This is an allowed energy level. Therefore, it must be accepted. If it's allowed, it must happen. The photon is absorbed, and therefore the photon also ceases to exist. The energy is given to the electron jumps up energy levels, and then the electron is unhappy. Electrons hate to be above the ground state and will do anything they possibly can to get rid of energy. One way of getting rid of energy is simply to emit it. So, the atom could just emit the energy and drop back down to a lower energy level. Well, how much energy would it emit? Remember, when looking at this diagram, these energy jumps don't move. The ground level, the second energy level, and the third energy level all stay in the same place, which means it's the same amount of energy to jump up as it is to jump down. There's the same distance between the rungs of the ladder whether you're going up or down. So, if the electron jumped back down to the ground state, the energy it gave off would be the exact same amount that it originally took in. And that energy correlates to a sky blue photon. Now remember, every color has its own wavelength, or you can think of it as every color has its own unique energy. So the color that it absorbed is the exact same color that it can emit. Now this would still be a brand new photon, but it would be the exact same color as the one that was absorbed earlier. Now if a lower energy photon came in, perhaps fire engine red, then the atom could absorb that photon, the electron would jump up. Notice this shorter jump. This tells you also less energy. Less energy is a shorter jump. Is this allowed? If it jumps you up to an allowed energy level, it is. So will it happen? If it's allowed, it must happen. But don't worry, because the electron hates it and has to get rid of it as quickly as possible. When it gets rid of it, it can jump back down, emitting the same amount of energy that it took in, giving off a photon of the exact same fire engine red color. Well, what if another red photon came in, and before you could get rid of it, a lime green came in? Is this allowed? As long as you're staying on those ladder rungs, as long as you're jumping energy level to energy level, it is allowed. However, you could also get rid of it by giving off lime green, followed by giving off fire engine red. Or you could drop straight down as a sky blue. This is a mix and match situation as long as you stay on the rungs. You can walk up the ladder, red-green, and walk down the ladder, green-red. You could jump up, sky blue, and jump down, sky blue. You could walk up, red-green, and then jump down blue. You could walk up blue and jump down green-red. But the key thing here is the exact same colors you absorb are the exact same colors you can emit. So the photons absorbed are the exact same as those you can emit. If you get a sky blue in, you can get a sky blue out. If you get a fire engine red in and a lime green in, you can get a lime green out and a fire engine red out. Same colors in, same colors out. So if you have a source giving all the colors of light on the left-hand side there, and all of those colors of light are going through a cloud of atoms there in the middle, well, what's going to happen is some of the colors will be absorbed by that cloud of atoms. And in this case, as the light goes through, it absorbed a sky blue. And you'll notice that over here, we are now missing a sky blue. And as the light continues to come through, you might lose a fire engine red, and you might lose a lime green. And those of us scientists sitting on the ground here at Earth are looking at that spectrum going, look, I see this pattern. Fire engine red, lime green, sky blue. I know what this is. I know what type of atom, I know what element has that pattern. And then we could identify the type of element. If you're not absorbing, emission will work the same way. So if you don't have a light behind this, you could still figure it out. Because if the atoms are getting light from somewhere, they could still then emit. And in this case, you could emit a sky blue, a lime green, and a fire engine red. And those of us scientists back on Earth would say, look at these colors. Oh, I know this pattern. I recognize this pattern. And we could then also tell what the element was without ever going there. So whether it's absorbed or emitted, it is the same pattern, and that's what lets us identify it. These are known as Kirchhoff's laws. So if you look at a hot source through a prism, what you're going to get is all the colors of the spectrum. This is called a continuous spectrum. If you look at a hot light through a gas, that gas will absorb some of the colors of the light, and then through a prism you will see all the colors except for the ones that were absorbed. This is called an absorption line spectrum or a dark line spectrum. If you look just at the gas without the light behind it, however it's getting light from somewhere perhaps off to the side, then this cloud of gas will emit. If you look at that emission through a prism, you will see only the emitted lines. This is known as a bright line or emission spectrum. And you'll note that the emission spectrum and the absorption spectrum are just the inverse of each other. So we can tell what the element is regardless of whether we see emission or absorption. In fact, if you put the emission lines on top of the absorption line spectrum, you would end up with a continuous spectrum.